Well, I devoted the last hour to persuading you that water has structure and describing several kinds of structures that have been proposed. I spent some time describing the possible arrangements of water molecules. I think that you can conclude from all of that that at least there's some kind of structure because of the huge void ratio, 38% water molecules in water that's virtually incompressible. There are other bits of evidence too, but that's perhaps the strongest. That is the strongest. The other really important point to remember is that there's very good evidence that, and other evidence, that water the molecules are strongly bonded to each other. That is, that there's some kind of bonding. So whatever the structure is, it must be a bonded structure. 91% of the bonds exist according to X-ray diffraction, or to infrared measurements, at melting. And we're concerned with temperatures below about 30 degrees generally, which means that we can regard water as something that's strongly bonded. Now, what all of this was done for was to prepare you for considering water interfaces, and particularly clay water interfaces, where gelling is a phenomenon, so that you'll have so much gelling. I wish it were more quantitative than it is. So I presented for you. These are the structures that I believe prevail, and others have structures that they don't really identify, but have some kind of properties, except Paulings, of course, who identified a class 3 type structure. Well, the reason that we're concerned with structures of that sort on, got it upside down, on clay molecules, clay particle surfaces, is that there's good evidence. I passed out a couple of papers that give it to you, that the water is bonded strongly to the clay surface, that at least one layer of water is bonded strongly to the clay surface. Now you can imagine that as being individual molecules or molecules with some kind of a structure. This diagram represents the clay surface bonds where there's an oxygen, oxygen, oxygen in the silica tetrahedra on the clay mineral surface. And these circles represent water molecules that you can see fit with every other molecule bonded, hydrogen bonded to oxygen in the surface of the clay with that same kind of structure. I didn't invent this structure exactly. Hendricks and Jeffries in about 1936, if I remember correctly, proposed a layer of water on the surface of clay, and they noted that you could arrange the water molecules in this kind of an arrangement and that it would just fit the surface with a little bit of stretching. They believed that the water bonds were all tetrahedral. That was a common perception then. In fact, some people still feel that water molecules have to be tetrahedrally bonded. So they postulated that these bonds were bent, and therefore weaker bonds, that they were bent at the surface. And their side view showed molecules, water molecules with bonds that had knees in them on the surface of the clay. If this is a clay surface, they had water molecules with bonds that were bent somehow to fit the surface. Well, there is one problem with this kind of a structure. And of course, the structures I showed you in the last slide would this kind of arrangement directly. They would arrange themselves, except for the fact that the spacing is such that they'd have to stretch. The bond lengths would be different than the bonds in water, and the resulting density of the material would be right at the surface of the mineral would be 0.95 grams per cubic centimeter. calculate that just from the geometry of the system, assuming that the bond to the clay mineral was that I prescribed earlier. So these bonds would have to stretch. It's interesting that Lowe made some ingenious measurements of the of the density of water molecules near the surface of clay, and what he found was that with distance from the surface, the density fell off like this, and 95 is about here. 0.95 grams per cubic centimeter, about here. So as close as he could get, it appears that the water molecules are in an arrangement that stretches the bond. So what's happening is that you have a rigid surface with oxygen exposed on the surface, and the hydrogen bonds conform to the molecules. Remember, we had 2.76 angstroms for the structures I showed you earlier, and this is stretched now to 2.94 angstrom. So it appears that this structure, or something very much like it, certainly can exist on the surface of the clay mineral. Lowe's paper, the one that I passed out to you, discusses the pressures that result from water being absorbed on the clay surface, the pressure in the clay matrix that's absorbed on the clay surface. In order to explain that, let's consider the surface of the solid and how it affects the water near it. First of all, the solid is, the amplitude of the thermal motions in the solid are very, very much less than the amplitude of motions in the water. Remember, with even visible particles, visible under a microscope, jiggle because of the thermal motions of water molecules. So the thermal motions must have at least the amplitude of those jiggling, or the amplitude of those jiggles. But the surface of a solid, on the other hand, is relatively rigid. It doesn't have much thermal motion. So the one influence on the water that the solid interface has is that it restricts its motion. I'll write that lower. By which I mean the amplitude of the motions are much smaller. The second thing is that the molecules are bonded, one layer is bonded to the surface. So there's an attraction by the solid to the surface. Now this structure that I showed shows the first layer of molecules on the surface. You can imagine that another layer can bond to this one with every other bond pointing downward from the layer on top of that. Or you can imagine the double or single layers like this lining up with the others, attracted by the van der Waals attraction between adjacent sheets. And the third factor, if you're willing to consider the planar structures that I described, is that it results in orientation. Of polymers, water polymers. So the solid has a major impact on the structure of the water near the interface. Now, next question is, how far does this extend? There have been a lot of measurements on properties of water near interfaces, glass capillary interfaces and clay interfaces, and they range in distance from about 100 angstroms, which is about 30 layers, to as much as a millimeter. That is, influence is considerable, which means that whatever the structure is on the surface, it's propagated outward to some extent, probably diminishing as the thermal motions and the competition by ions for hydration affect that structure. So you can expect some kind of an exponential decay of this structural arrangement that exists on the surface. The paper that I passed out to you last time by Lau attributes swelling pressure to this growth of water in the on the surface of the clay. That is the orientation and structuring of the water on the surface of the clay. He says that, and he makes pretty good arguments. He's got about 10 papers out that essentially make this argument from different directions, that water accumulates or orients itself on the surface of the clay particle, and as it arranges itself, it exerts a pressure, like pressure of crystallization of solids. You know, when ice grows in a pipe, it cracks the pipe, you know, because it expands. Well, all crystals actually have a pressure of crystallization that will force how shall I say it? We'll put pressures on their environment. Cracks in rocks, for example, result from pressures of crystallization. So that you can imagine that water molecules that are accumulating on the surface underneath the ion cloud that we described, exerts a pressure, and that can be responsible for gelling. If you consider two-dimensional description of clay water, a saturated clay water system, then immediately after it's disturbed by shearing, you'd expect there to be a mixture of ions and water in the spaces between the clay. There's some water undoubtedly bound on the surface initially. If you put let's say a low concentration of clay particles in a suspension in an electric field, they'll migrate, and you can calculate the apparent diameter of those clay mineral particles, and it shows that there is some water that moves with the clay. That is, the apparent diameter is larger than the clay. So there's undoubtedly, even initially, some water absorbed to the surface of clay particles, but most of it will be in some kind of an arrangement. As the water accumulates on the surfaces, however, and creates pressure, then you'd expect it to inflate the structure. That is, to press outward and to make it more nearly a card house type structure with layers of water next to the mineral surfaces and the free water and ions in a like the filling of a sandwich in between. Now this is a remarkably stable structure. If the ions are concentrated out here with the negative charges here and negative charges here, charge attraction adding to to hold us together and opposing the swelling due to the water. Now the question is, how do they get from here to here? Well, it's a thermal process. As water molecules fit into this structure and exert their pressure, the clay particles are pressed and become kind of a card house structure. Day's paper, and Day and Riddle's paper, and some others show that the least disturbance of this breaks it down and it has to reform again. Remember when we talked about the swelling experiments or the disturbing experiments, the soil or the sediment actually takes water from the measuring device, from the tensiometer, after it's deposited and while it's forming this gel, which supports this kind of an argument. I invite you to read Lowe's paper, the one I passed out to you, and read his arguments for that, for the swelling pressure. Now I must, before leaving the subject of swelling, tell you what other people's arguments are. And their arguments are that this mixture of ions and water creates an osmotic pressure. You all know what osmotic pressure is? Remember from physical chemistry? It's the pressure that results from the attraction of the ions are hydrating and creating a pressure. So it's a little less satisfying to me in this water structure theory. Well, I think you'll find Lowe's paper convincing, and it'll be useful to us. The important part of all this discussion is that this gelling takes time, and that once it's taken place, it tends to stabilize the deposit, makes it less subject to consolidation than it would otherwise would be. And what you'll find if you take a core sample of estuarial sediments, a cohesive sediment, is that it's a gel, and it shows these effects with very small changes in density with depth. Now there is change right at the surface, which I'll talk about in just a minute. Let me repeat one more time. The important feature of gelling, the important part of gelling is that it takes time, and it results in a stronger material more resistant to erosion. It's almost complete in most systems. Now, of course, because it's a thermal process, it's very sensitive. We'll talk about that a little bit later. Well, with that preparation of discussion of gelling and the changes in a sediment bed, let's talk about erosion of sediment beds. Gelling and the changes in a sediment bed, let's talk about erosion of sediment beds. There are many investigators of sediment erosion and soil erosion. I'm sure you've heard a lot about it. But one method that's commonly used is to use a flume like that we use for position of studies of deposition, and to prepare a bed either by letting it deposit slowly from flowing water, or to put all the material in suspension and stop the flow and just let it settle out at zero velocity. Then to increase the velocity to some level at which it will begin to erode, and I'll put time on this axis. And the concentration in the flume, concentration of suspended solids in the flume on this axis. And what you'll find is that at zero time, being the time that you increase the velocity or raise the velocity to a level where it will erode, is that the concentration will go up something like this. And if at that point you increase the velocity still further, what you'll find is that it'll go up or something like that. So you can, and of course, at this point, you've eroded some depth into the bed, and at this point you've eroded to a greater depth into the bed. Well, the first reaction to seeing data of this sort is to say, well, it must come to some kind of an equilibrium. But of course it can be that the bed is less and less erodible with depth. And so that what you're doing is seeing a changing erosion rate as depth of the bed is, more of the bed is eroded. And then as you increase the velocity, you erode it to a still deeper depth.
Is there step changes in velocity you're suggesting, or are they continuous?
This is, let's say at this point, this curve is measured at, let's say, 0.4 feet per second in the flume. And then the velocity at this point has changed to 0.6 feet per second. And then up here you might change it again to 0.8 feet per second. So that the shear stress is being increased in steps. And it's held all during this period at 0.4 feet per second, during this period at 0.6 feet per second. Well, the other possibility is that there's some kind of an equilibrium developing between the material being suspended and material being deposited. So to investigate that, we let it erode for a long time at a constant velocity, 1.14 feet per second, in that same plume I told you about earlier. I've forgotten how this was deposited. It's in your report that you have. But notice, this is a log-log scale, and notice that after something like 800 hours, it was still rising on this plot. What's happening is that this curve doesn't really level out. It just gets flatter and flatter, but it never quite gets to zero. So that this is just an empirical plot of the data that shows that it doesn't ever quite level out. It continues to erode. Well, to investigate that further, we eroded in steps, like those that I described there, and plotted the steps. And a curious thing appeared. I'm pretty sure that the velocity was zero at the end of the last deposition period, so that material settled in the return line. And when the velocity was increased from 0 to 0.34 feet per second, the concentration raised up to this level and just stayed there, so that material in the return lines was resuspended. Now, the fact that it resuspended it all at once, unfortunately we don't have any data in there. That's minutes. So the first reading was 2 minutes after, and the circulation time around the flume was about 1 minute. So it was just maybe 2 circulation times around the flume. But that brings up an important point, this first curve here. There's two mechanisms of erosion. The first one I'll call bulk erosion. And that occurs when the shear stress applied to the surface exceeds the shear strength of the bulk material. And if the bed strength increases with depth, then what will happen is that instantaneously material, that is, when the shear stress exceeds the strength of the bulk sediment, instantaneously the material will be suspended down to the depth where the shear strength equals the applied shear stress. So that's an instantaneous process, and by instantaneous, it really is instantaneous. In experiments in the flume, when we had the water perfectly clear and you could increase the velocity fairly quickly, what you would see is little tornadoes in the water, and instantly that portion of the bed would go into suspension. It's really quite a sight. But in any case, bulk erosion is when the shear strength of when the shear stress applied by the flow exceeds the bulk shear strength of the sediment. And the other is called surface erosion. And this is a particle by particle erosion. So and this is really what we are observing here, surface erosion. So if you increase the shear stress from 0 upward, nothing happens until the shear stress exceeds the critical shear stress of the surface, of the clay surface. Then with increasing shear stress, there's increasing surface erosion. Then when the shear stress exceeds if you continue to increase the shear stress, when it exceeds the bulk shear strength of the material, then the material will go into suspension all at once. Well, that's what we're seeing here. we eroded at least the material in the return line and possibly some of the bed.
Yeah, I was going to ask about that. Why that sort of explains what's going on in the return line. Wouldn't you expect the same would you expect the same deposition to have occurred in the bulk of the plume versus the return line?
Well,
if that's happening in the return line, wouldn't it also be happening in the main part of it?
Recall the return lines were made to have a higher shear stress than the bed did, so that we wouldn't have deposition in the return line. But by stopping the flow when there was still material in suspension, we left some in the return. Well, the only importance of this is to point out that that occurs, that bulk erosion occurs. There's lots of other evidence for it, lots and lots of evidence for it occurring. And notice it didn't increase. After that material came into suspension, it came in, and after 2 minutes it didn't increase any further. So we just had this material going around in suspension. Then we increased the velocity. See, that was 0.34 feet per second. We increased it to 0.82 feet per second. And immediately, as quickly as we could make the measurement, the concentration jumped from about 0.07 grams per liter to about 1.6 or 1.7 grams per liter. So we had more of the bed, some of the bed actually went into suspension instantaneously. But then after that point, we had a log increase like that plot I showed previously, which meant that surface erosion was taking place. You all follow the experiment? Then after letting it run for some time, the velocity was increased to 1.33 feet per second, and the concentration here is about 1.0. So it didn't jump up like it had here. It stayed the same, and it followed a log plot to this point, and then it seemed to go at a different rate. What do you suppose that caused that? Anybody have any ideas?
I didn't understand the question.
What do you think caused this curious change here? This concentration at the end is about the same as this one, and then it eroded for a time for about 20 minutes at this rate, and then it eroded at a faster rate. What appears to be happening is that when you let it run for a long time, this was 1,000 minutes, so that's about a day, something like a day. When you let it erode for a while, there must be some interchange of suspended particles with the bed. That bond long enough to resist shear stress stick. In other words, you get a kind of a bed armoring, and it's probably a millimeter thick, if that, a very small bed armoring. The change in concentration here is quite small between here and here. So it's just a thin surface must develop with prolonged measurements like that. Well, then the same thing happened here again. And 1.33 feet per second is above the velocity in the flume at which net deposition would take place. Now you can argue, you can say, well, maybe that fraction of the bed that had a more resistance was left, but I don't think so. I think because the concentration was the same, and because it took only this distance, that the armoring takes place. So there must be some interchange where that small fraction of the particles that can stick under that condition do stick. Well, so we have some kind of a phenomenological description of what's going on there, and we have this empirical relation. So we can it seems to fit right down to 1 minute here. The one calculation time is the strength of the bed at that depth. Do you follow me? We know what the shear stress was, and we know what the strength of the bed was at that depth. And the result of numerous experiments led to this complicated plot. This is, raise that up a little bit. This is a plot showing shear stress on the bottom and concentration in the flume. So we're not measuring the depth of the bed eroded directly, we're just measuring the result of its erosion, the increase in concentration in the flume. And quite an increase. This is grams per liter, so we got up to maybe 10 grams per liter, so that's about the total material in the flume was 21 grams per liter, so that's about half the material, half of the bed was suspended. And what we found from a number of beds that were deposited under a variety of conditions, and they're described in the report, is a number of, recall now these points, each of these points was determined by the intercept on that line, giving us shear strength at some depth in the bed. And they all seem to fit linear, everybody else's data presently, which also seems to fit linear relations. This curve and this curve are measurements on beds that were settled at zero velocity. That is, all the material was put in suspension and allowed to settle till the water cleared, and then the flume was increased in steps, as I described earlier, and each point was determined. Same sediment, but this one has a steeper slope and a lower than this one does. The difference is that this was done at 4 days, and this was done at 26 days, I think, so that the bed was allowed to gel or consolidate and gel. The other curves, this one is a little bit confusing, but these two other curves were measured on beds that were formed under by depositing during flow, so under some shear stress. And you can see the surface, there was a slightly consolidated layer, then at greater depths it increased roughly parallel to. It would be in here somewhere. Now, an interesting thing, the intercepts correspond to the different orders of the shear strengths of the different orders of aggregation we discussed earlier. Recall the table in the rheological study report that showed that for San Francisco Bay we had a 3.9, 1.4, 0.8, 2.36 shear strengths of aggregation, and this is about 0.39. This one comes down at about 0.8. 0.8. This is about 1 point far from 1.4, and this one is about was the first order 3.9. Well, 3.9 would be here. Remember, the bed is one order of aggregation stronger than the same order of aggregation of the particles. So that tends to support the notion of orders of aggregation. Also notice that there's a layer at the surface that isn't as strong as the deeper area, as there's this kink. Now I'll show you some other experiments that were measured by Professor Matus. This is like the plot I showed you there, the time, concentration of material circulating in the flume, and he increased the velocity in steps. He allowed consolidation for 5.6 days for this one. Now he's got two plots here. And I don't recall what the reason is. I'll give you the paper to read for the second plot. But essentially you can see what he did was, as I described earlier, instead of extrapolating back to the beginning as I did, he used the flat part assuming that that was the point at which the bed, that there was some kind of a steady state. So he didn't actually reach that steady state in some cases. But in any case, using that, he came up with a shear strength of the bed in newtons per square meter, as that was dynes per square centimeter. So this is about 2 dynes per square centimeter as a function of concentration. And you can see he got the 2 lines like that described earlier. So evidently, and this is, of course, a thin layer of material on the surface of the flume. This is Dr. Parshur's data. He calculated because of the change in density with depth, the actual depth of erosion that those 2 straight lines indicate. And he found, for a number of experiments, and he found that for different times of consolidation, this is 1 day, 1.7 days, 3 days, and finally 5.6 to 10 days, that the strength of the bed increased with depth more strongly as the material aged, that is, as it gelled. The depth here, notice this is 4/10 of a centimeter. So we're talking about a thin layer on the surface eroded this way. Okay, so what we have is 2 mechanisms of erosion, bulk erosion and surface erosion. And that the bed shear strength increases with depth for a short distance. Now, actually, I haven't shown you further, but it doesn't increase much with depths thereafter. That is, it tends to stay about the same. And the reason is that the gelling pressure keeps it from collapsing. There are sediments under roads, say across Arcata Bay, where they're concerned about the consolidation of the material under the road. They've measured the density of those sediments for something like 30 years, and it doesn't change. You know, it consolidates to a point, and then it just stays right at that depth. And it's pretty open. It's like 70% water by volume, you know, kind of situation. Now, what we need to do now is to consider ways of determining what those shear strengths with depth relations are, or shear strength relative to applied shear stress. Well, the rate of erosion for surface erosion I'll write this up to emphasize it. Was given first, I think, by Parthionides, although several people did it, as, I'll call it erosion rate. This is grams of sediment per square centimeter or meter per second is equal to a constant, like is m, times the shear stress, applied shear stress, well, relative to a critical shear stress. You usually see this CE, critical shear stress for erosion, -1. All it says is that the excess shear stress, and this is for tau W greater than tau CE. Up to some point, if we plot applied shear stress against erosion rate, E dot, that nothing will happen up to some point, and then above that point, it will increase linearly. This is M. This relation works quite well. Tau phi, the critical shear stress erosion, remains constant. But as I just showed you, it doesn't remain constant at the surface. Below that centimeter or so, it's more nearly constant. But but right at the surface it doesn't remain constant. So one of the problems with this is that you need to determine this empirically, and of course this empirically. This was presented by Parthenides. Who's at the University of Florida. He did it well, he was at Berkeley. And you'll find this commonly used for surface erosion. For bulk erosion, the time rate of change is instantaneous. So all you need to do is determine the shear strength as a function of depth of the bed, and you can calculate the consequence. Actually, you have to determine the shear strength as mass of material from the bed. But remember, the concentration in the suspension went up linearly with time, so it's not as complicated as it seemed. Okay, this really works well when the shear strength is reasonably constant with depth. It doesn't work very well at the surface, but it turns out you don't very often need to determine it at the surface. That is, for a thin layer of sediment, it's usually not a critical matter. You'll see Parthenides' relationship presented often in modeling of cohesive sediment transport. Well, this works well for estimating erosion rates under uniform flow, or at least flow that's uniform for a time long compared to the time for erosion. For tidal flows, it works quite well. But we have another phenomenon in estuary that is very important as far as erosion is concerned, and that's erosion under waves. Let's consider the San Francisco Bay system. I think most of you are familiar with the plan form of San Francisco Bay. It's the Central Valley of California, something like this, with Sierra Nevada mountains that all drain into the valley in various ways. And a main river is the Sacramento River, comes down and goes out through Carquinez Straits. Let's see, the delta is down in here. And goes out through Carquinez Straits into the Napa River comes in here, and the bay, San Pablo Bay, looks something like this. Maybe I better make it a little bit larger. And then central San Francisco Bay and the Golden Gate. It's a pretty crude picture, I'm afraid, but looks something like this. I have the bay very large compared to the valley. I want to talk about the valley, the bay. But we have essentially, and Suisun Bay is up here, essentially we have a sequence of bays that are connected by relatively narrow openings. There's a Treasure Island in here, and Alcatraz in here somewhere, San Francisco here. We have a very seasonal precipitation in California with rain and snow. And the rainfall runs off, that is not trapped by dams, during the winter, and the snow runs off during the spring when the snow melts. So we have a very large input of water during the winter and early spring months. Most of the sediment, about 90% of the sediment, comes out of the Central Valley during those months. There's a little sediment brought in by other streams, but it's minor compared to the amount that comes from the Central Valley. This sediment is 80%, 90% clay and silt, about 60% clay and about 30% silt. The rest is fine sand as it comes out here. And that material deposits first in these upper bays where the salinity is high enough to cause cohesion and the velocities are low enough to let it settle. And there's a large deposit in these upper bays during that time. During extreme events, material can be carried clear out into the ocean. But by and large, most of it's deposited in these upper bays. It would stay there. There's up to 2 foot of new sediment in San Pablo Bay at the end of a spring runoff during normal years, not during drought years. And that would stay there if it weren't for the fact that the material is suspended by daily onshore breeze-generated waves that occur every day during the spring and summer months. It's only late in the fall that you don't have them. So you have these daily onshore breezes, and they suspend this fine material and keep it in suspension while the slow tidal currents carry it down in the system. I don't want to get off into San Francisco Bay yet. I'll give you a whole lecture on it sometime. But the system is resonant to the tides so that it actually has a standing wave in it. The amplitude of the tide down here is about 2 feet greater than it is at the Golden Gate. And this standing wave of water causes flow past it's out of phase with the tide going in and out the Golden Gate, carries sediment past Treasure Island down into South Bay and vice versa. At night when the wind dies and the waves die, material that's suspended in the shallow areas deposits in these shallow areas and then is again suspended the next day. So we have a gradual progression of this during the year down into the system. The bulk of this, the peak comes in about March, and the peak arrives down here about June. So that there's a net transport through the system, and the portion of it, of course, goes in and out through the Golden Gate. About half the material that comes in, or did in 1956, the last time we had a balance, about half the material that comes in from the Central Valley goes out to the ocean, and the rest stays in the bay. I'll give you more details on that. What I wanted to show later, what I wanted to show you was that suspension by waves is a very important part of our transport circulation in an estuary. San Francisco Bay is not unique in this regard. You can go all around the country and see estuaries, Mobile Bay, Chesapeake Bay, all the little bays on the side, Delaware Estuary, all have this same kind of circulation where suspension by waves is important. Well, you may remember from 260, and a portion of you didn't take 260, so I'll have to go back over it, that we can describe shear stress on the bed of an estuary as a function. This is still water level. That is the level the water would take if there weren't a wave on it, and we have some depth. The height of the waves, we'll call this capital H, and the length of the waves. L, and we have another parameter we'll call a period, T, and that's the time that a progressive wave, the time between the peaks passing a point of a progressive wave, peaks of a progressive wave passing a point as they're propagated. I didn't get that quite right. But in any case, we have all those parameters, and we can describe a simple wave as we can describe the whole wave underneath as first of all being something like a circle right at the surface. That is, a particle of water follows a circular motion, which becomes smaller and more elliptical with depth, which at the bottom just is a back and forth motion, perpendicular to the wave crest, in the direction of propagation of the wave. And we can describe the velocity in these motions, and at the u is equal to pi h over t times the hyperbolic cosine of 2 pi d plus z, where z is the divided by the hyperbolic sine of 2 pi d over L times cosine 2 pi t over t minus x over t, x over L. We're interested in the case where d is equal to z. Z has an opposite sign, so this is 0 and this whole term is 1, leading us to u head equal to pi h over t times 1 over the hyperbolic sine of 2 pi d over L. And we're interested in the peak value, so I'll call this UB max. And the peak value occurs when this term is 1, right? So we just have 1 out there, leaving this relationship. Let's see, I described H and T. L is equal to the period times the square root of the velocity of GD, the velocity of the wave. And I think I've defined everything there. So we have now the UB max is the peak value. Water moves back and forth, but it goes through a maximum velocity in one direction, then it slows and reverses, goes to maximum velocity. It reaches a maximum velocity in the second direction, back and forth that way. So we have a peak velocity that can erode the material. The shear stress is proportional velocity squared, so UB max squared. So we can say it's tau is max is equal to some constant times u squared. So substituting this here, we have the peak shear stress is equal to pi h over t and 1 over with some kind of coefficient out here. Are you all familiar with hyperbolic sine, hyperbolic? Anybody not? Don't hesitate to raise. You're not? This is e to the 2 pi d over L minus e to the minus 2 pi d over L divided by 2. They're called hyperbolic sine, hyperbolic cosine, hyperbolic tangent because they have the same relations to one another as sine, cosine, and tangent. And if you're interested in complex particles, there's a direct relation between the sine and the cosine. You know, z minus minus e to the minus iz over 2I is equal to sine of v, and so on. There are relations that fit one another, just like the geometric tangent, sine, cosine, and tangent relate to each other. It's useful here because it
I had a question for you. I'm a little unclear why the cosine term drops out. I'm not sure.
it becomes 1 at
Oh, you mean-
at its maximum value.
Okay.
It's 1. We're interested in a maximum. So that we have a way of describing the shear stress, the peak shear stress under waves. Now, our problem is that we have shear stress due to wave action and shear stress due to the currents going on it. We have to combine those. The shear stress due to the current can be described as rho u star squared, right? Current. But the currents and the waves are rarely in the same direction. So we'll have a shear stress due to the waves, let's say in this direction, and perhaps one due to currents in this direction. You can move a vector around, remember, so I'll put them both at the same point. And the sum of these will be something like this. You'll have to use vector addition for these two, wave and current. So the sum will be something like this. And there are lots of ways of summing vectors, but probably the easiest one is to put the tau max, if you like, is equal to the square root of the tau max wave squared plus tau current plus 2 times tau wave times tau current times theta 1, theta 2 minus theta 1, let's say, the 1/2 power, Earth. This is theta 1, this is theta 2. The difference, the angle between theta 1 and 2. This is just the law of cosines. But in any case, it's necessary in modeling suspension by waves to get the result of the two. Now, it turns out that most times the currents, the shear stress due to currents is small compared to the shear stress due to the waves. So that typically you just have the shear stress under the waves, but there are cases where you need to have both. Well, before I go into this term is important. What it shows is that as the depth gets greater, the shear stress becomes less. Since it's 1 over here. And it turns out that when the depth is greater than about half a wavelength, you can neglect it altogether. So that concerned about really shallow water conditions. Now, San Francisco Bay system is about 70% is less than 5 meters deep, I think, something like that. It's really a shallow bay. And those mudflat areas I described are all very shallow. One time we were doing some research out on San Pablo Bay, and we wanted to set up instruments on a platform out in the shallow part of the bay to observe suspension by waves. And we persuaded the Hamilton Field rescue personnel to take us out on one of their crash boats, because it was a boat that could get across the shallow water. And what it was a long speedboat about from here to the wall that had a great big aircraft engine mounted in the back and a big propeller on it. And my impression of that trip was, Professor Orlov and I went out on it together, was that we went through the waves rather than over them. That boat just screamed across the top of San Pablo Bay, and it was terribly wet. But it drew only about this much water, so you could go right up into the shallow areas with it. Well, this is actually important for materials. It's not used for surface erosion for reasons I'll describe in just a minute, but it is very good for bulk erosion. And it turns out that bulk erosion is a problem. Materials really put into suspension in a hurry in these really shallow areas. When the shear stress is less than the critical shear stress for bulk erosion, the sediment undergoes a peculiar phenomenon, and you can see this in a flume quite easily in a flume. It's hard to observe in nature, and that is that the sediment actually moves in an orbital motion like the water under a wave. This sediment, this isn't quite flat here. There's actually some depth to the orbit, and the sediment itself will undergo an orbital motion. I once put false pearls next to the wall in a flume, in a wave flume, and watched it move, and you can actually see the pearls follow this, the sediment follow this kind of a motion. And that, because the sediment typically is gelled, what that does is it just destroys the structure of it, even that small motion, and it fluidizes the material at the surface. Develop, if there isn't much of a current there, a turbid layer that's quite shallow, and it just stays there. If there's a current to wipe away, of course, it will take it away. But it just becomes fluid. I have a paper to pass out to you that will describe that. The fluid layer, because it's more dense than the layer above, doesn't mix upward very well unless there's enough strength of the current to carry it up above that. There have been some recent measurements made on Lake Okeechobee in Florida that show this phenomenon. They put out turbidity sensors and measuring devices in the sediment, and they actually see this phenomenon of fluidization. But bulk erosion is the most important part. Well, I want to save the last few minutes to talk about our field trip. I got my calendar out, and I hope you all did, and I would like to make it either let's see, this coming Saturday is that's day after tomorrow. That's a possibility. Or the 16th, I'll be leaving for Washington. The 23rd is Saturday. The 23rd would be okay. Or December 7th. Any one of those sound good to you? 23rd?
What time would you expect to return?
The field trip?
Yeah.
We'll leave about 8 and get back about 2 or 3 in the afternoon. 23rd? Everybody agree on the 23rd? Okay, Saturday the 23rd. That was easy. I'll arrange for a couple of cars, and we'll just take 2 cars. See, we have 17. We'll take 1 car. I'll make 2 vans. Then the other thing I want to do is pass out these papers. So. Yeah. All right, it's, well, it's cosine. Well, a vector this way and a vector diagonal. We could draw this as a parallelogram. So A, let's say, and this one is B. And all cosines would be this one's times 2 times this times the cosine of B. But if you want to use this angle, you have to use plus.
That should be a cosine of that angle. Oh, I see. If you want to use that, I got you. That should be a cosine of that angle. Yeah, it should be a cosine.
Oh, cosine, yeah. Here.
Right. And
Thanks.
should be tau squared there.
Let's be square.
What?
Thank you.
The relation for you. The relation.
Uh-huh. This one? This one?
Is that the minus z?
This one? Z is positive.
So that's going.
So when Z equals D, this is 0.
It's only that's minus.
Zero.
So it's D minus
D minus z.
D minus Z?
Yeah, or measure Z up.
Measure
Or
Z
measure
up.
the upper.
No,
Well, if you make Z positive, no, you're right. You're right. You're right. Yeah, if you make Z positive upward. There you go. Thank you. I should have caught that. I've got about 7 more minutes, so I'll take up a closely related topic to erosion, and that is dealing with slurries. We deal with slurries commonly in dredging processes where the material is pumped up from the bottom with perhaps a cutter head on the end of the intake, and then pumped through some distance of pipe into a pond and allowed to settle in the pond. And there's one of the things you need to know is what's going to happen in the pond. There are 2 ways of operating ponds. One is as a sedimentation basin with continuous flow, and the other is on a batch basis. And I think more and more in the future, operations in a batch basis with, say, alternate ponds being filled consecutively. And the reason for that is that the regular agencies are becoming more and more concerned about the turbidity in the water coming out of the pond. Most ponds are not very efficient. You know, they're just diked in areas with pipe discharge in one end and a weir at the other end, and water just so that the turbidity is quite. One way you can examine the separation of the water and then just take samples of the sediment at the concentration of the actually discharge concentration isn't very steady usually, but you can high and low values if you like, and putting the material in a fairly large diameter and observing the way it consolidates, just as we did with that bottle of water there. And you'll find that there's a couple of empirical relations that describe that settling. It's if you plot a log plot, log time versus log H. Column might look something like this. And the water surface up here, and H is the height of the top. The sediment with that image that you can generally see. What you see is that there's some confusion right at first while an aggregate is forming, and then a steady interface, and then it will change. Like slopes. Now this was first described by Work and Kohler. And their papers in Fundamentals of Industrial History about 1950. But they noted 2 slopes. You may find another slope out here. As the material consolidates, it goes through this collapse of the larger pores first, as we discussed already. Have a relation that way. Another relation was, and his is this H divided by H infinity, which is the height it will reach eventually, minus 1 is equal to a constant time after it's mixed up. In your report, you'll find on page didn't bring a slide of it. Page 5, you can just note it and look at it. plots of Bosworth's relation for different depths of material. And what it shows is that it fits reasonably well. It's a plot of 1 over T of volume or height. One against H here. What you get is that starting at certain times is in another line like this. And for different heights, for a greater depth, something like this. Again, you get this collapse. Because it's a plot of 1 over T, this part is compressed down here at later times. So you get reasonably good straight lines. And the theory presenting behind this is that when H, so which is 0, otherwise it's empirical.
Wouldn't K be negative? If H is...
K be negative?
Oh, I'm sorry, H. I'm sorry.
This is negative.
I was thinking I had the terms switched around. I was thinking H infinity was larger than H.
Well, when you plot it this way with positive 1 over T increasing this way, then it's positive. Now both of these work when the concentration is low, to describe it, when the concentration is low enough so that the aggregates can form early in the settling process. What you have is settling, and then until aggregates are stacked on top of each other, and then once there's enough overburden pressure, they begin to collapse, and that's why you see this section here. So in regimes 2 and 3 that I described earlier for deposition, this is the kind of relation that you'll get. If you have a higher concentration, higher than about per liter typically, then the particles don't get a chance to form aggregates very quickly. That is, they're in each other's way, so they can't really form aggregates. And you have what we typically refer to as a slurry. And if you try the same experiment with a slurry, a high concentration greater than about 10 grams per liter, greater than about, probably 15 is a better number, grams per liter. If you plot log H against time for this, material, what you'll find is that H will stay constant for some time. That is, there won't be any change at all. It's like our settling experiments, and then it falls off in a straight line log way. So this part we can describe as H, log H is equal to log B minus K T, where this is our K here. If the depth is greater, then what will happen is that this curve will fall off the same, but it will take a longer time. And the reason for this is that in order for channels to form up through this clay mixture, it takes time and thermal motions that will let small channels form between some kind of aggregates. And then once they form, then you get this log decrease, just like the case of work in Kohler. The way you determine these is by experiment. You take the material, it's a simple experiment, mix the material vertically in the column, and then measure the height as a function of time. If you, in this relationship, also empirically, if you plot the concentration versus B, to get B as a function of concentration, it appears to follow a straight line like this. That is, the time goes up with the concentration. Well, I've already taken more time than I should, but let me put one more thing on the board to help you with your homework. For uniform steady flow, we can describe the shear stress on the bed as equal to rho g times the hydraulic radius times the slope. Remember? Remember this? So we can describe the slope as equal to rho g r over tau. And r for a wide flow is the same, virtually the same as the depth. So we can say this is approximately equal to rho g d over tau. Oops, I have it upside down. Tau over rho g d. That's it.
One R and one D.
No, there's R, the hydraulic radius is the cross-sectional area divided by the perimeter. And for a wide one, it's just the depth. There's not much, I'll put this R. I'm sorry I kept you a little long today. We'll work on it. I'll see you all on Tuesday.
That's right. This is the hand that passed out. So this is
Can I ask you a math question?
Sure.
Since you brought up
Just a second, let me get this put away for you. I'm not a mathematician.
well, I understand. That's why I want to ask you.